Chapter 11. I think, yeah, chapter 11. This is section 1 on gases and pressure. In the chapter States of Matter, you read about the kinetic molecular theory, which is based on the idea that particles of matter are always in motion. In this section, you will study the implication of the kinetic molecular theory of gases. You have learned that the temperature of a gas is related to the kinetic energy of the gas molecules. In this chapter, you will learn about other properties of gases, including pressure, volume, and amounts of gas present, and the relationship between these properties. This is where we're going to start learning about the gas laws. Now, I'm assuming you have a bit of background with pressure and force from physics. So we understand that if you blow air into a rubber balloon, the balloon will increase in size. The volume increase is caused by the collisions of molecules of air with the inside walls of the balloon. The collisions cause an outward push or force against the inside walls. So if I ask you what creates pressure, I want you to talk about the collisions of gas particles against the walls of their container. Pressure is the force per unit area on a surface. So we know pressure is force over area. The SI unit is the Newton, although in chemistry we very rarely use Newton. At Earth's surface, each kilogram of mass exerts 9.8 newtons of force due to gravity. So the ballerina is a good example of how surface area is related to pressure. So when the ballerina is on both flat feet, the force is 500 newtons because that's based on her mass and the force of gravity. So the area of contact is 325 centimeters. So 500 over 325 is 1.5 newtons per centimeter squared. That is the pressure that is exerted on her feet. Now, if she goes up on her points on 2 toes, that decreases the area of contact from 325 to 13. So now we have 500 newtons over 13, which is 38.5. So you can see how much the pressure increases by going up on her tippy toes. And if she goes onto 1 toe, the area of contact is then halved to 6.5. And you can see that the pressure is nearly doubled. Gas molecules exert pressure on any surface with which they collide. The pressure exerted by a gas depends on volume, temperature, and the number of molecules present. And the gas laws that we're going to be studying in this chapter will reflect each of those circumstances. A barometer is the device that's used to measure atmospheric pressure. The scientist who basically discovered how to measure pressure was called Torricelli. That's why one of the units of pressure is called the torr, T-O-R-R, based on Torricelli. So what he did was he sealed a long glass tube at one end. So this end is sealed and this end is open. And he filled the tube with mercury. He held the open end with his thumb and then inverted the tube into a dish of mercury without allowing any air to enter the tube. When he removed his thumb, the mercury column in the tube dropped to a height of 760 millimeters above the surface of the mercury in the dish. He repeated the experiments with tubes of different diameters and lengths longer than 760, and in every single case, the mercury dropped to a height of 760. So the importance of this experiment is that he discovered that atmospheric pressure was what we call 760 millimeters of mercury, or 760 torr. So when you have atmospheric is the pressure due to the atmosphere, right? So when he has the open tube at this end and he doesn't have any air at all in the tube, and he puts the tube in the dish of mercury, the atmospheric pressure is going to push down on the mercury in the bowl. And of course, we know that pressure is transferred through a liquid. So the pressure from the atmosphere is going to be transferred to this liquid, and it rises to a column of 760. So atmospheric pressure is 760 millimeters of mercury, or 760 torr. And that's based on Torricelli's experiment. They're two different units for pressure. There's actually like 5, but there's only 1 or 2 that we really use with any common purpose in chemistry. I think physics you use Pascal a lot. I don't like Pascal. So these are all of the units of pressure. We have the Pascal, which is equal to 1 Newton per meter squared. The millimeter of mercury, torr, they are the same. And then we have the atmosphere. This is the most used unit of pressure in chemistry. I'm not sure about physics, but 1 atm is equal to 760 millimeters of mercury or torr, because remember those 2 units are interchangeable. It's also equal to 101 kilopascal, or 1.01 times 10 to the 5th Pascal. So there's lots, there's 5. There's 5 different units of pressure. There's going to be a lot of conversion problems that we're going to be doing, and like formulas when we get into the gas laws. You can determine what unit of pressure you feel most comfortable with, but understand that you will have to be able to convert between the different units. So you have to remember that 1 atm equals 760 millimeters of mercury or torr, and it equals 101 kilopascals. I don't think you're probably going to see pascals very often, if at all, but these are like the 4 main ones. So we have the millimeter of mercury, we have torr, these are have the same scale. 1 atm, like I said, is 760 millimeters of mercury, and of course the SI unit is the Pascal. Now, one thing that we do have to remember when we start doing gas laws is something called STP. STP, which is standard temperature and pressure. For purposes of comparison, scientists have agreed on standard conditions, and the standard temperature and pressure is 1 atm and 0 degrees C. So if during any problem that I give you and I stipulate STP, that should automatically tell you what the temperature and the pressure is immediately. 1 atm, 0 degrees C. Now, Dalton found that in the absence of a chemical reaction, the pressure of a gas mixture is the sum of the individual pressures of each gas alone. The pressure of each gas in a mixture is called the partial pressure of that gas. So Dalton's law of partial pressures is the total pressure of a mixture of gases is equal to the sum of the partial pressures of the component gases. It might sound complicated, but it's actually pretty simple. The law is true regardless of the number of different gases that are present. So we can express Dalton's law as PT, or total pressure, is equal to P1 plus P2 plus P3, yada, yada, yada. So here we have a flask that contains 0.12 atmospheres of oxygen, okay? We have a second flask that contains 0.12 atmospheres of nitrogen. When we mix the two, we just add the pressure from each of those molecules. So even if you take all of the oxygen molecules out of here, then the pressure that's left is the pressure from nitrogen when it's by itself, 0.12. So nitrogen by itself exerts just as much pressure as it does when it's mixed with another gas. And the last topic for this section is gases collected by water displacement. Gases produced in the laboratory are often collected over water. So you can see here, we've got a chemical reaction that's going on inside the flask, inside here, and hydrogen gas is being released and is being bubbled through water, and this is the water vapor that is mixed with hydrogen gas. The gas produced by the reaction displaces the water, which is more dense, in the collection bottle. And you can apply Dalton's law of partial pressures in calculating the pressures of gases collected in this way. A gas collected by water displacement is not pure because it's always mixed with water vapor. That is because water molecules at the liquid surface evaporate and mix with the gas molecules. I talked about this in the last chapter when I talked about equilibrium vapor pressure. So because you have water here, water molecules at the surface are going to evaporate and mix with the gas that's being collected. So you have to use Dalton's partial pressure to calculate the pressure of your gas that's being collected. Water vapor, like other gases, exerts a pressure known as water vapor pressure. Suppose you want to determine the total pressure of the gas and water vapor collected inside the bottle. You would raise the bottle until the water levels inside and outside the bottle were the same. At that point, the total pressure inside the bottle would be the same as atmospheric pressure, which is PATM. According to Dalton's law of partial pressures, the following would be true. The PATM would equal the pressure from the gas that you've collected plus the water vapor pressure. Now we know water vapor pressures at certain temperatures, so we can just use this table to calculate the pressure of the gas that's collected. An example, oxygen gas from the decomposition of potassium chlorate, KClO3, was collected by water displacement. Their barometric pressure and the temperature during the experiment were 731 torr and 20 degrees respectively. What was the partial pressure of the oxygen collected? So you are given the total pressure, which is atmospheric pressure, at 731 torr. And we look at the table for the water pressure of, for the vapor pressure of water at 20 degrees, which is 17.5 torr. And we know that PATM is equal to the pressure from the oxygen plus the pressure from the water. So our unknown is PO2 in torr. So we just rearrange the equation to solve for PO2, and we get 731, which is the total pressure, minus the 17.5, which we get from the vapor pressure of water table, and we get the pressure of O2 is 713.5 torr. Let's do another example. Some hydrogen gas is collected over water at 20 degrees C. The levels of water inside and outside the gas collection bottle are the same, which means that the total pressure is equal to atmospheric pressure. The partial pressure of hydrogen is 742.5 torr. What is the barometric pressure at the time the gas is collected? So we go to, we've got PATM equals pH2 plus pH2O, because we're collecting hydrogen gas and they want to know what this is. The partial pressure of hydrogen is 742.5. So that's equal to 742.5 torr. Now I have to go back to the vapor pressure of water table and find out what the vapor pressure of water at 20 degrees C is. Oh, okay. Let's go back here. 20 degrees C, 20 degrees C, yeah, okay, is 2.3 kPa. Shoot, remember that, 2.3. Whoops, wrong one, my bad. There we go. Okay, so we've got 2.3 kPa, but we need it in torr. So how do we convert kPa into torr? So we're going to have torr on the top, kPa in the bottom. So I'm going to do 760 per 101. Because I'm just relating it back to 1 ATM. So 760 torr is equal to 101 kPa. So then I need to get out my calculator. Where's the calculator? I'm just gonna use my phone. Ooh. Okay. A little bit disorganized. 2.3 times 760 divided by 101 is equal to 17.3 torr. So that would be 17.3 torr. So that plus 742.5 is equal to 759.8 torr. Yeah, close enough. And we'll do one more. Helium gas is collected over water at 25 degrees C. What is the partial pressure of the helium given that the barometric pressure is 750 millimeters of mercury? Okay, so again, we're going to use, I'll do blue this time. We've got PATM is equal to P, this time it's helium, plus P water. We want to know what is the partial pressure of the helium. So I'm just going to rearrange the equation so that PHE is on the other side. So PHE is equal to PATM minus PH2O. And this says barometric pressure is 750. So this is 750. Now we're in millimeters of mercury. And now I have to go back to that table to find the vapor pressure of water at 25. So let's go back. 25, 3.2. Remember 3.2, 3.2. Okay, 3.2 kPa. And we're going to convert that to mmHg. Again, it's 7. What was that? Oh, okay. 760 mmHg over 101 kPa. So again, with a calculator, 3.2 times 760 divided by 101 is equal to 24. Well, the answer's already there, but anyway, 24.1. So that would be 750, and I get 725.9. And so the only reason why mine is a little bit different than this is because I rounded the kPa.